Okay, so I'm open to questions.
I have one.
Yes, absolutely.
It's from the Lewis Structures Lab. I was
Okay.
wondering when we're estimating the length of the bond.
Hmm.
When they're equivalent structures, we use the average.
Well, let's talk about that.
I'm just wondering because when they're not equivalent and you have one that's more electronegative, if you use both of them still, like for the um
If they're equivalent, what you want to do for the bond length is say it's the average. It's based on the bond order. So let me do a share here, and let me show you. Okay, so you should be able to see my paper now. Is that what you're looking at?
yeah.
Paper in my hand. Okay, so uh, I'm trying to remember the one that I was looking at yesterday. Um, maybe it was N2O.
Yeah.
So
Yeah.
if you look at N2O, which has 10 plus 6 electrons for 16 electrons,
Right.
nitrogen goes in the middle because it is the one that can make the most number of bonds. Nitrogen makes 3 bonds usually. Oxygen makes 2, and that's enough to say we're going to put nitrogen in the middle. You put the one that makes more bonds in the middle. Another way to say it is you take the atom that is less electronegative and you put it in the middle. Okay, so when you put 16 around this, you get this and this. So here's 16. And then to make an octet on nitrogen, which is what you normally want to do with things in period 2, is you have a number of choices. So here's one choice where you take 2 double bonds to make a triple bond. And with all the choices, you always put this double-headed arrow because it indicates what's called resonance. Another choice is this, where you have 2 double bonds to the middle nitrogen.
You would even put those arrows on ones that you exclude at the end too.
Well, right now I don't know what I'm excluding, so I'm just putting the arrow down. It's because I don't know what I'm excluding, if that makes any sense.
It does.
Okay, so here, when we assign formal charges here, we get a 0, +1, -1, -1, 0, 0, ooh,
Yeah, and
+1. There's no reason for that one to change because it's got 4 bonds here and 4 bonds here.
right.
Uh, +1, +1, and -2. And all the formal charges should add up to 0 because there's no charge on this thing. So here, we're going to eliminate that guy altogether because we do not want charges of -2, period. No ifs, ands, or buts.
Right.
So here we have a tie between these two. Now, since we don't memorize bond lengths, and let's pretend we don't know what the bond lengths are. In that one problem, let's pretend I didn't give you any bond lengths, okay?
Okay.
Just because I don't want to look them up. I'm too lazy. But nonetheless, if these two structures are both important, and they're both important because they both only have one formal charge at 0. They both have formal charges that are either 1 or -1, and no -2s or +2s. So they're both important. But we like this one better. And we like this one better because the -1 is on oxygen. And over here, the -1 is on nitrogen. And we always like the resonance structure that has the negative formal charge on the most electronegative atom.
Right.
Now, when we look at electronegativities, you might want to memorize a few electronegativities. And I'm going to go down here and show you the most electronegative atom is fluorine. And they actually assign them values. So fluorine is a 4. Oxygen's a 3,5. Nitrogen's a 3,0. Carbon's a 2,5. What's next to carbon? Boron?
Yeah,
It's a 2,0. And then over here, what do we have?
beryllium.
Lithium, beryllium. Beryllium is a 1,5 and lithium is a 1,0. Now, why do you think I'm showing you this particular row? 2 reasons. We see a lot of compounds with these elements in there, especially these last 4. And
Okay.
secondly, look how easy it is to remember those.
Right.
They go down by halves.
Okay.
Fluorine is the most electronegative atom. Oxygen is second. I think chlorine down here is a 3,0. And you might think, oh, so do these go down by 1s? And they don't, because like bromine is like a 2,8 or something like that. But it is important to know that electronegativity is when you go in a group, it's more electronegative at the top and it's less electronegative at the bottom.
So then it would be closer to the one with oxygen having the -1. It's not just the average of the 3 bond order plus 2 divided by 2 is what that is.
Well, see, that's just it. It's not always the case. So here, look at the electronegativity difference here. 0.5 is not a big deal. You know, a 1 is a pretty big deal. A 0.5, that's not bad. In fact, when you look at hydrogen, which is a 2.1, most people consider the carbon to hydrogen bond to not be that different as far as electronegativity goes.
So we can treat it as the same and just do
well, here's what I would say is this one is better because the -1 is on oxygen, but it's not better enough to just, you know, dance around jumping saying, woo, 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 this one's better. It's more like a, that one's better. It's kind of, I don't know if you ever go to the optometrist for an eye checkup, but they always do is 1 better or is 2 better. And this is one of those ones where you go, 1's better. And, but it's not to the point where you would say, you know what, it's just a toss up. You would say 1 is probably better. Now, to determine how long the bond is, so this is something that we talk about later in the chapter. We talk about something called bond order. And I'm going to get on a new piece of paper here. We talk about bond order, bond length, and bond strength. So for bond order, I'm going to give you 3 examples here: a nitrogen-nitrogen single bond, a nitrogen-nitrogen double bond, and a nitrogen-nitrogen triple bond. Notice when I'm comparing bond order, bond length, and bond strength, we're looking at 2 identical, well, you can't see that, I'm sorry. We're looking at 2 identical atoms. So I could have also done this if I wanted to. I could have done CN, C double bond end, or C triple bond end. The idea here is that whatever 2 atoms we're comparing them all the way across. So a carbon and a nitrogen, carbon, nitrogen, carbon, nitrogen, or nitrogen, 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 etc. So here the bond order is 1, regardless of which one you have here. It's a 2, regardless of which one you have here. And it's a 3, regardless of which one you have here. The bond length, since we're not memorizing numbers, you would say that this one is the longest, this one is the shortest, and this one is the midlist. And I don't know if you guys know my position on midlist, but if you don't, I'm the midlist child. And I hated that there was an oldest kid and there was a youngest kid. And I'm not an ist. I'm the midlist kid. Oh, he's the middle kid. I'm the midlist. All right. So bond strength, this is the weakest. This is the strongest. And of course, what is this one?
Middleist.
The middleist. It's a new word. It's sweeping the nation. Okay, so it doesn't matter how you compare these, whether it's you're comparing carbon nitrogens or nitrogen nitrogens. This is the trend. Okay, now from that, what do you do if you have something like this? So I think I've switched the two. I had the nitrogen triple bond on the left before, but now I've got it on the right. So here, when we look at bond order, this is a 2, this is a 2, this is a 3, and this is a 1. Did you follow me there?
You do, yeah.
Okay, but the idea is that this structure is not correct, and this one is not correct either.
Right.
Neither is correct by themselves, but together they represent the molecule. So here, what do we actually give for the bond order for this nitrogen-nitrogen bond, which is sometimes like a double, sometimes like a triple? And when I say sometimes, it's really a meshing of the two. Now remember, we liked this guy better, and this one is worse. But again, not jump up and holler and say, woo, 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 this one's better, but yeah, kind of better. So here we would say the bond order is kind of like a 2.5, and I'm going to say ish. Now, why am I saying ish?
Well, because it's not exact, because it's a average of the two.
It's an average of the two, but one's a little bit better than the other, right? And so what would this one be? 1.5-ish. Okay. Yeah. So what we would expect if we did not know the bond lengths is we would say we expect the nitrogen-nitrogen bond length to be longer than a nitrogen-nitrogen double bond or nitrogen-nitrogen triple bond, because the triple bond is the shortest, right?
Right.
So we'd expect it to be longer than a nitrogen-nitrogen triple bond, but shorter than a nitrogen-nitrogen double bond. And the reason we say it's shorter than a nitrogen-nitrogen double bond is because it's like a 2.5, not quite a 2. And let me change this a bit so that you can see what I've written. Okay, so when we look at the actual problem, it actually gives us the bond lengths. And I believe this one is like a 115 and this one's like a 147. Yeah, a triple is a 115 and a double is a 147. And the actual is like 124 or 125 or something like that. So it's actually closer to the triple bond, which we might expect because this is a better structure, right? Right. But when we look here, we would say that we expect the nitrogen-oxygen bond to be longer than what? Longer than a nitrogen-oxygen double bond, right? Right. And shorter than a nitrogen-oxygen single bond. And it is, but it turns out that it's actually closer to the double bond, which is kind of amazing if you think about it, because we say this one's better, this one's worse, right? Right. It's actually closer to the double bond. I don't remember what the numbers are, but it's clearly closer to the double bond one. And so this is one of those things where you don't really place a whole lot of trust in your ability to figure the actual bond length. And so you end up saying this kind of stuff, that your expectation is going to be longer or shorter than this. Now, last night I was explaining that you may want to say that also that, you know, maybe the reason it's more like this one is closer to a triple bond is because if you take a look at this nitrogen on the left, it's got the number of bonds it likes to make. 3. And so maybe that's why this one is better. The nitrogen in the middle has 4 bonds, but that's a push either on the left or the right. The nitrogen in the middle has 4 bonds. So you can't say, oh, that's the deciding factor, because it's not. And then here, this oxygen on the right has the number of bonds it likes to make. So maybe that's why it's more closer to a double bond in character. But nonetheless, this is absolutely correct based on the numbers you see, is that the bond order tells you that it should be, in each case, a little bit longer than the 3, or here longer than the 2, and shorter than the 2 or shorter than the 1. So
For the nitrogen bond length, would you want to do the length that you have for the nitrogen double bond plus the length that you have for the nitrogen triple bond, and then divide that by 2?
If you wanted to give a specific number, yeah, I would add the 2 together and divide by 2 to get an average.
Okay, so you can do that and this explanation too.
You can do that, but what if you're not given the numbers?
Right.
Then you write down something like this.
Okay.
Now, if we actually take the numbers, which I believe are 115 and 147, and add them together, you get 262. You end up with 131 as the average. And the actual bond length here, I think, is 124, which is clearly closer to 115.
Okay.
So this is the nitrogen triple, if I remember the numbers right. Nitrogen double. This is the average, and this is the actual.
I think that one was for the nitrogen oxygen single and double.
Oh, was it 115 and 147?
Yeah, I'm looking at the lab right now, actually.
Oh, okay. What was the nitrogen double?
120 picometers.
And how about the triple?
110.
110. So the average would be 115. And what was the actual?
Where is it?
Usually they're quite a bit different than this.
It says the N only the single bond is given with 112.
The N single bond of 112. Let me take a look real quick. I'm going to do a new share. Boom. So here's my browser. Here's the class. This is module 8 homework, or is this this is the Lewis Structures lab, right?
Yes.
Okay, yeah, the numbers are actually, the nitrogen double bond is 120. The triple bond is 110. Yeah, you're right. And it's 112. So that is closer to the triple bond length, right?
Yeah.
So the average is 112, and oops, I'm sorry. The average is 115. It's actually 112, which is closer to the triple bond length, right?
So when it says actual bond length, it's not saying that's a single bond. It's saying just a bond between a nitrogen and a nitrogen, and a bond between a nitrogen and an oxygen, that dash in between.
That dash is the number. Well, actually on, where it says 112?
Right.
The dash just means that the actual bond length, without regard to whether it's a double, triple, or whatever.
Okay.
Okay.
Yeah.
So it's not saying it's a nitrogen single bond. It's saying the nitrogen to nitrogen bond is 112. Okay.
Mm-hmm.
So I don't know how you draw like a 2.5 bonds, but this is not okay. So for this guy, where it's actually 112, this is not okay to do.
Should we be looking at your screen?
You should be, but you're not, because I didn't switch. And I'm glad you brought my attention to it. Still in the waking up stage. This is not okay. Doesn't that look like 2.5 bonds? But it's not okay. And the reason it's not okay is because a single electron that's not paired with another one has a particular meaning in chemistry. And it means it's a radical, a free radical. And if you know anything about free radicals from just when they talk about foods, you don't want free radicals in your foods. They're bad. The reason they're bad is because they react with everything. They don't care. They will react with anything. And when they react with things, they tend to turn them into things that they shouldn't be. So if you have a free radical inside of your cell and it's reacting with things in your cell that it shouldn't be, it's destroying things in your cell. And what makes them even more dangerous is that when they react, one of the products is another free radical.
So is that what is something that can cause cancer?
It could cause cancer, yeah. Well, mostly what we're talking about is it's destroying things in your cell. And the only way for a free radical to finally be put to rest and say, okay, it's not going to cause any more harm, is if a free radical with one electron reacts with another free radical with one electron, and together they make a pair. And then you no longer have the free radical. So free radicals are rare, and they can cause a lot of damage before they run into another free radical. And that's why they're really, really bad. They like to react. And I'm giving free radicals personalities. They don't have personalities. They just react. They react because they're not stable. And the only way to make them stable is when they react with another free radical. So they're not really good. So that's why we don't draw this.
Okay, so I guess that answers my question then. Even though the one that has the negative charge on oxygen is more electronegative, you still do the average of both of them.
Yeah, if you're going to put a number out there, you just say it's kind of around, it's near that average. So our average is 115. We'd say it's near that, right? And the actual number is 112. Is that 115 a pretty good guess?
Pretty good, yeah.
It's a pretty good guess. And if you look at the nitrogen oxygen double bond versus triple bond, and we look at the numbers, so I'm going to do a new share again and go back to those numbers. We see that it's actually 119, but here for the double bond, it's 115. For the single bond, it's 147. And the real one is 119, which is closer to the double bond, right?
Yeah.
So I'm going to go back to what we were just looking at. So here it's 115 and 147, and the actual is, well, I got an extra L in there, is 119. And if you split this down the middle, the average would be 131. So, the only thing you can really say about this one is, well, golly gee, it is between these two numbers, but in this case, it's a whole lot closer to that one, right?
Yeah.
So our guess of 131 would be kind of a little off. We'd be better off guessing, oh, it's more like the double bond. But you don't know that. It's hard to gauge these things because there's probably another molecule out there where you have a carbon, a nitrogen oxygen double bond, and a nitrogen oxygen single bond where they resonate, and it's not this case. It might be closer to 131. I don't know. Okay, so you don't want to get too tied up in trying to actually pick the number. It's better to give a range.
Okay. And it would be closer to the ones with the stronger bonds, which is just the bond order increasing.
Certainly in this example, that seems to be the case.
Okay.
But I don't know if that's the case in all the examples. Because we haven't looked at them all, right? We'd have to look at case after case after case and look up bond links and compare them. And I'm not going to do that. I'm not that interested, to be honest.
Okay.
But you're welcome to do it. and tell me what you find out.
Thank you, Tony.
You bet. So Issa, did that all make sense to you?
Yeah, I think I'm good on the lab.
All right. And I just posted your that lab that we talked about yesterday. Which one was that? Yeah, that was the Lewis structures ones. And I cut out
Same lab.
I cut out the bat stuff.
You cut out the bad stuff? What bad stuff?
The bat stuff.
The what stuff?
Bat.
Oh, okay, okay. Got it.
Okay. All right. Rebecca, more questions? Issa, more questions?
No, I'm just getting into the second part of the chapter.
I guess I have kind of one question. So when you're talking about the, gosh, what is it called? The molecular geometry of molecules. When you're figuring out what it is, basically you just go by how many pairs there are. Because it's kind of hard for me to tell the difference between like the, the bent 109.5 and the bent 120, other than just seeing that one has 3 pairs and one has 4.
Okay, so here's how you get molecular geometry. First, you need a Lewis structure. And that includes resonance structures if they have them. So that's the first thing you need, is you need a Lewis structure. Then you get the electron pair geometry. And this gives you the angles. And then after you get the electron pair geometry, you get the molecular geometry. Okay, so I'm going to show you how to do this 1, 2, 3 with 3 molecules, and show you that you get 3 different molecular geometries, but they each have the same electron pair geometry. Okay, so we're going to look at the following, and I'm going to do 1, 2, 3, 1, 2, 3. So one molecule is going to be CH4. Now this is what the Lewis structure looks like. And when you draw the Lewis structure, you might think, oh, this thing looks flat, because that's the way it's drawn. And in fact, it's not flat. It is not like this. That's not what it is. Okay, that's the way it's drawn, but this is wrong. The actual structure looks as follows. Luckily for me, I have my models here so I can put them together. And I think that these would be great toys for young teens, but horrible toys for very young kids, because all of these pieces you can fit into your mouth. So if you had very young kids, they would no doubt eat these. This is the actual structure. Do you see that we have 4 hydrogens bonded to a central carbon?
Yeah.
So here, this is the Lewis structure. The electron pair geometry, we would say, looks like this. So this is the Lewis. This is the electron pair geometry. And what are the angles here? Well, here the angles are 90 degrees. Here the angles, if I hold this so that you can see the angle, you can see that it is more than 90 degrees. And it turns out that's 109.5. And any 2 of these angles is 109.5. So if I rotate this, you can see that that's still greater than 90.
Yeah.
If I rotate it again, that's still greater than 90. No matter how we rotate it, it's 109.5. It's kind of like a Snickers bar. No matter how you slice it, you always come up peanuts.
It was easy for me to figure out like how you get the 120 degrees and 180 and 90. But I couldn't figure out where the 109.5 comes in. I mean, do we
Well,
just memorize it?
you have to memorize it.
Because
It's
the
a,
other ones make more sense.
yeah, the other ones make more sense because it's based on the unit circle. And all the other ones are based on you having all of your atoms in the same plane. So here, do you see that we have all of the atoms in the same plane here?
Right.
And here, if we take a look, we can see that these angles are really close to one another if I line them up. Can you see that?
Mhm.
But, you know, if I line them up, we can actually see that the top one has a little bit of a smaller angle than the bottom one, right?
Right.
So you can't figure this out, this angle, uh, unless you're really good at geometry and figuring out, well, what would these angles be when it's not in 2 dimensions, but it's in 3 dimensions? And you can probably use some geometry type theorem to figure it out. And it turns out to be 109.5. Okay, so this is what it is when you have that. And it's bigger than 90, but it's less than 120, but only slightly less than 120. And I would argue that 109.5 is only 10 away from 120. And it's about 30 away from 30, it's about 20 away from 90, right?
Yeah.
Okay, so it is closer to the trigonal planar. So here, this is where we get the angles. And again, you can't, it's hard to figure out that angle, so you memorize it. And my trick for memorizing it is that there's a radio station in Humboldt County. It's 109.5. And they play tetrahedral music. In fact, it's a 109.5 smooth tetrahedral. So that's how I remember it, because it sounds stupid, but you know what? There you go. Now, I was hoping to do a 1, 2, 3 like I have up here, 1, 2, but I've run out of room. So for the molecular geometry, actually, I guess I will put it right here. This is what you do. Now notice with the molecular geometry, I'm no longer using teardrops. I'm actually putting bonds in.
Right.
So you see this teardrop that is coming towards us, you put in a wedge. And this teardrop that's going away from us. So here's the teardrop coming towards us, right here that I'm pointing at.
Okay.
And here's the one going away from us. For the one going away from us, we put dashed lines. And when I say going away, I mean this teardrop is going away from us when you look compared to the central atom. So do you see how this is coming towards us right here?
Yeah, that's why the triangle is bigger towards our end.
And you understand the triangle is based on this idea here.
It's just point of view.
Yeah. What I like to teach people about this is this point right here is called the infinity point, because it's infinitely far away from you, supposedly, right?
Right.
And what's really cool about this is the following. Have you ever seen that symbol on the back of a car?
I'm probably not the one to ask about that.
It's called an infinity. You ever seen those cars with those symbols on the back?
I probably have.
Well, they're drawn like this, where this is a small distance and this is a great distance, because that's the infinity point. And when it goes back up, this is the horizon, so it gets a little smaller. And they took artistic license and called it infinity with what is this, 4 I's instead of a Y on the end. So now that you've seen this, I've got to warn you, if you see an infinity driving down the road, don't tailgate it so you can look at the symbol, because you're going to get into an accident. And then even worse, perhaps, is If you see one in a parking lot, don't get behind the car and let it back up over you. So maybe you just Google the symbol and you look at it. And this is by far, to me, the coolest car symbol out there. It's probably even better than the BMW one with the blue and white. Okay, so this is CH4. We call this tetrahedral 109.5, and the angle comes from the electron pair geometry. So now I'm going to do another one here, and I'm going to raise it up a little bit like this. So NH3. Here's what the Lewis structure looks like. Now, what's the electron pair geometry going to look like? It's going to look like this. So do you see that the electron pair geometry is identical to the electron pair geometry for CH4?
Right.
Except for you got nitrogen in the middle. So this is 109.5, smooth tetrahedral. But now we need to put these bonds and lone pairs in. This is by far the best way to draw this. Put the lone pair at the top. And what you're supposed to think here is that that looks like a three-legged stool with a couple of raisins on the top of the stool.
Raisins?
Well, dots, right?
Yeah.
Grapes, olives. Okay, now here, what are the angles? They're 109.5. They're actually not 109.5. They're a little bit less. But I want you to memorize 109.5 because they come from this.
Okay.
We call this trigonal because of the three-legged stool, and pyramidal because it looks kind of like a pyramid. Now, the third one I'm going to give you is H2O. H2O looks like this. That's the Lewis structure. When you look at this, it looks like all three atoms are in a straight line. But they're not, because each one of these sets of electrons repels the other sets. And that's the origin of this shape, is that these lines here represent electrons that are pushing the other electrons away, but they're all still have to stay attached to this central atom. So imagine if you had a twin that you really didn't like and you're walking around with your mother and you guys wanted to get as far away apart as possible and mom was holding on to each of your arms. What would you do? One of you would be on one side of mom, one of you would be on the other side of mom. And if one of you moved closer, the other one would counter that by moving farther away, right?
And that's why they don't stay on either side. They go to one, the top or bottom, however you do it.
Yeah, so the idea is that they're going to be as far apart away as possible, because the farther apart they are, the less repulsion there will be. So here, these lone pairs, the dots and the bonds, are trying to get as far away as possible, and this is it. So this is the electron pair geometry for H2O, and the angles are 109.5 tetrahedral. Now, what is the best way to draw this one? And the answer is this way. And this one we call bent 109.5. Now, you see how I drew this one and I drew this one? I said, these are the best ways to draw them.
Right.
Let me show you bad ways of drawing them. But before I move on, they all have the same electron pair geometry, but they all have different molecular geometries. The reason they're different is because they have a different number of lone pairs on them. Here are 2 lone pairs, here 1 lone pair, here none.
Right. Okay.
So that's why they have different molecular geometries, because this molecule doesn't look like this. This molecule looks like this. Now, you might be saying, well, where are the lone pairs? Well, let me show you where they are. Actually, let me show you this guy And let me show you the lone pairs.
Those look pretty fun.
They are.
I do
So-
remember using those in high school.
So do you see this guy here? This is what this guy looks like.
Okay, yeah.
So do you see the lone pair right there?
Mhm.
Now, the lone pair isn't a big old long stick sticking out into space because the lone pair is not attached to another atom. It's stuck on this one. So it's kind of like a little hat
Right.
compared to this guy here, which is more like this guy here. You can tell those look different, right?
Right.
So what about H2O? Well, H2O, I actually have right here. And here, for the lone pairs, I just put dots on here. So do you see 2 dots and 2 dots?
Yes.
So if I wanted to, I could make the H2O like the other ones. Okay, so here's an H2O. Now I'm going to put lone pairs on this. So I'm going to get rid of that guy. I'm going to put a lone pair on this. So don't be surprised when I do this. There's a lone pair. And I'm trying to get another lone pair. But when you put lone pairs on, they are hard to take off.
Hey, Tony.
Yeah,
I have a kind of a question related to that about H3O plus.
sure.
Would that be the same shape as this? Because
Well, it's a good question. We'll answer that in just a moment. Okay, so there you go. This is H2O. So wouldn't you say that these 3 things look different from one another?
yeah,
So this is tetrahedral, the one I'm tapping. Trigonal, pyramidal, because if you look at it from the side, it looks kind of like a 3-sided pyramid. And this one we call bent, because if it looked like this, we call it straight. And here, when you bend one down, it's called bent. And this is 109.5 because they're all based on 4 pair. Okay, now you did ask about the H3O plus compared to all of these, and let's take a look at that, okay?
okay.
So first of all, the Lewis structure is going to look like this. And with the Lewis structure, when there's a charge on it, you put brackets and the charge on the outside. Okay, so this has 4 pair on it. 1, 2, 3, 4. So that means the oxygen is going to be shaped like this. And we call that tetrahedral. And what are the angles here?
109.5.
Okay, now, if you really want to remember it, you got to say it like the radio station.
I don't think I have a radio.
109.5. Okay?
All right.
I mean, I'm serious. It'll help you.
I think I'm gonna remember it after this.
109.5. Coming to you from Humboldt State. And it's the chemistry radio station. Bringing chemistry to you 24 hours a day. All right. So here, what is the best way to draw this guy? And here's your answer. Put the lone pair up here, a hydrogen here, and a hydrogen here, and a hydrogen here. And then, of course, we have to do this. What do we call this shape? Which one of these does it look like? The one here with the blue center, this one here with the black center, or this one here that's supposed to be like water.
The pyramid.
Pyramid. Yeah.
So this is trigonal pyramidal. And if you want to sound snooty, what do you say? You say trigonal pyramidal.
Yeah. How do you pronounce that? Pyramidal or pyramidal? Like, I don't know.
Tomato.
I always struggle with like chemistry pronunciation.
I say pyramidal because I know the word pyramid.
Pyramidal. Yeah,
So,
that's true.
Pyramidal. Right?
Mm-hmm.
So that's the way I do it. I've heard people say pyramidal, and that may be actually correct. I don't know.
Does chemistry have like a book of pronunciation or something like that?
Well,
to assist people?
I'd love to write one. So this is trigonal pyramidal, and what are the angles? Well, if this is 109.5, what are these angles?
All the same.
109, and you know what? They're not 109.5, but they are darn close. Now, I said this is the best way to draw it, right?
Right.
Let me draw up for you 3 other ways that are not as good. So here, I'm going to put one of the hydrogens going straight up, one of the hydrogens going to the right, one of the hydrogens on the wedge, and the other hydrogens on the dashed line. Do you see how this one, it's probably easy to say, oh, it's a 3-legged stool with a couple of raisins on top?
Yeah.
Does that look like a 3-legged stool with a couple of raisins on top?
There's no depth.
Not quite, does it? So I'm going to say that one's not as good as this one for people to see what's going on. Now, here's another way to do it. Let's put the raisins on the wedge and the other one on the hydrogen going back. Is that as easy to see what's going on as this one down here?
No.
No. And then, of course, the last one that I could show you is that I'm going to put the lone pair on this hydrogen coming forward. And this one is actually not too bad. It doesn't look like a 3-legged stool with raisins on top, but what it does look over is a kicked over 3-legged stool, doesn't it?
Mm-hmm.
So this one's not bad, but I think this one is by and far the best. Right. So whenever you're drawing these things, you're always competing with where do I put the lone pair so it's easiest for people to understand?
Yeah, I struggled with that with the equatorial ones and the octahedral. Whatever.
Well, for those, it's a clear bet on how to do that. So what you're talking about for the octahedral one is one that looks like this. I call this the dragonfly. And the dragonfly, because dragonflies have like 2 sets of wings, right?
Yeah.
And then here's the head and the tail. I remember as a kid always trying to play with dragonflies. So here's the dragonfly, if you will. This one, there's no equatorial and no axial. I mean, it looks like these 2 are axial because I can rotate this around the axis, right?
Right.
And what I'm going to do here is I'm going to take this white sphere off and this white sphere off, and I'm going to put 2 green spheres on it. And here you can see that quite obviously they're axial, right? Here's the Earth spinning on its axis, and here's the equator, right?
Right.
Because there's no way I could grab another 2 of these and it would look like an axis and everything else on the equator, right? Oh, there is.
Well.
So this one, they're all axial.
So that's why you don't have to put them towards the equatorial spots, because.
Well,
For the trigonal bipyramid ones.
This one, there's no axial and there's no equatorial.
Okay.
So this is with 6 things attached. There's no axial, no equatorial. So with these guys, when you put a lone pair on them, the best place to put them is on the bottom. Because then you could have the wedge, the dash, and the line straight up. Now for this one, that's this guy right here, which I'll put together. This one does have an axial and an equatorial, because there is a clear 2 that are axial. And when I get it put together, you'll see that. So remember the last one I tricked you. I had the 2 green ones and I said, clearly these are axial and you couldn't grab another 2 and make that happen. So I'm going to grab another 2 and you can see that, oh, that's not axial. They're not opposite one another, are they?
It makes sense because there's 6 pairs and it's circle. It makes sense.
Yeah. This one, there's only 5 pairs. So you're going to have 2 that are opposite and 3 that make a, what I call a propeller.
Okay.
Okay. So here we know that you're always going to put the pair on the equatorials. So here it's probably better to start this guy drawing it like this. Draw it like that, where the triangle is going up and down instead of left and right. And so here the first pair goes on an equatorial. And that's what you get. And we call this seesaw. And I think seesaw is another name for something that as a kid we called them teeter-totters.
Yeah.
So this is a teeter-totter. And here, the way I've drawn it, you can really see that, oh yeah, it could rock back and forth on these 2 legs, right?
Right.
Now, when you draw the second one, the next lone pair also goes on the seesaw. But on this case, what you want to do is put the lone pairs on the wedge and the dash. And if we rotate that 190 or 180, I'm sorry, you can see that this is T-shaped. So here I'm going to rotate it. Right? And you see why we call it T-shaped?
Yeah.
And then the last one, if you put the last pair, it's also going to go equatorial. And so here we call this linear. Liner, linear, because they're opposite. And the reason we put the lone pairs equatorial is because lone pairs repel better than bonding pairs. And so you want to get as far away from everything as possible. And the best way to judge it is how many 90-degree angles there are. So in this case, you got 2 90-degree angles. Whereas if we had put the lone pair here and kept the others, see here we're putting the lone pair axially, which is no good. You got a 90-degree angle here, a 90-degree angle with that, and a 90-degree angle with that. 3 90-degree angles. Here you've only got 2. So when you have such small angles, there's a lot of repulsion. 3 very repulsive events versus 2 means this is better. And this is not. So with these, Rebecca, the way to remember them is that if you're going to put lone pairs on this guy, you always put them in an equatorial position.
Okay.
And so here, I like to do this as abbreviations. AX for axial, EQ for equatorial.
Right.
And it took me a while to figure out that equatorial is not equatorial. It's equatorial.
It makes sense. Yeah.
Whereas, usually in chemistry we use equivalent, right? And that's an I. But
Right.
this word is based on the equator, which is an A. Right? Everyone wants to pass the equator sometime in their lives. Maybe I'm just projecting, but it'd be cool to go across the equator sometime in your life.
Yeah.
And if you've been to Australia, you've done that. What was it? I can't remember who, but someone said that they were on a ship and they actually passed the equator. They were in the Navy or something like that. Oh no, I get it. It was a Tom Hanks movie where he pretended to be on a ship. And he said that the first time he passed the equator, all of the senior Navy men were saying, look, we want you to stay up and look out at the ocean and let us know when you pass the equator, because you're going to see a line around it, just like you see on the globe. And he said, of course, you never saw the equator. All right. But that sounds like something a Navy man would definitely do to another Navy man, is tell him, hey, you haven't seen the equator first. You got to stay up and check it out. All right, then. I don't know. Does that help you with the shapes? Now here, what are the angles?
For the tetra 1, 2, 3, 4, 5, those ones are 90 and 120.
And 180.
Yeah. For the equatorial ones.
Yeah. And so here you can see it's 180. Here they're all 90s and 180, right?
Right.
And here it's the same as this one. So here, what are these? These two are 180. These two are 120. And these are 90s. Is this helping you at all, Issa?
Yes, this is helpful for me. I'm just kind of like taking it in.
Now, what do you think is the best way for you to understand what's going on here and to see it? And the answer is get out some vegetables and toothpicks and make these things. Like, what makes a really good central atom is a slightly softened carrot. And I don't mean like a whole carrot, but like you chop it up and you use a little cube for a carrot. Soften it up because it's easier to stick the toothpicks in, but don't make it too soft because no one likes mushy carrots. Even kids don't like mushy carrots. And then carrots are really good because when you stick the toothpicks in them, they kind of stick and stay. Grapes don't work so well because once you stick 6 toothpicks in a grape, they all soften up the grape and they don't hold their shape. Or you could use clay and Q-tips, or whatever. It's kind of fun to make these models, and you don't need to spend $100 or $50 on a molecular model kit.
Or do you? I'm just kidding.
I didn't buy this. My department bought it. So, here I am. I teach chemistry and I didn't buy that thing. All right.
They might have maybe something online. Like I would imagine that would be some kind of software online that they have to help you visualize.
You can definitely buy this online.
No, I mean like software, like virtual, like software where you can build it yourself.
You can, but you know what? When you build it in 3D, it's
better, yeah.
It's not as good as building it with pieces. They teach anatomy, I think, now using software where you can see the body and see sections, but it's not as good as getting in there and looking at the cadaver and seeing the pieces and how they fit together.
Yeah, it's not the same.
It's not as good. If I were a person being operated on, I would not want the person to have only been trained on the computer and they say, oh yeah, I got this. I would not want that to happen.
It's like they have what is it? a lot of simulation video games now for like to learn how to like
Oh, yeah.
operate a helicopter or like an airplane.
Yeah, one of the first simulations was a flying simulation, and
Mhm.
it worked wonders for getting people to get used to the controls. But they always followed it up with not the simulation, but the real thing, so that you, instead of getting used to the controls and where everything is, you actually get used to the feel when you're moving through air. So, but they're even getting better now. Now the simulations, the controls can actually simulate what it would feel like if you run into a gust of wind or something like that. So, but I don't think it's as good as the real thing. And besides, if you're going to fly, I want to fly. Okay, what else can I help you all with?
Those are the only questions I had for today.
That's it.
Yeah, I don't really have any particular questions yet.
Okay, so we're at 7:06, then we may as well cut it.
Yeah, I'm gonna take a look at some of your other videos and just start working on some problems or
So there was a Q&A where we kind of reviewed electron pair geometry and molecular geometry. And that will certainly help you with the lab for today, which is about molecular geometry, electron pair geometry. But today's lab does a little bit more. It also talks about molecular polarity. And when you read through the chapter, you'll see that they treat it a certain way. And when you look at my lecture notes for molecular polarity, it's pretty straightforward the way I do it. So watch the videos and you'll see how I do it.
sounds good, Tony. Thank
But
you.
before I do that, I'm going to tell you this: to get to molecular polarity, which is a hugely important topic, to get to there, first you have a Lewis structure. Then you get the electron pair geometry, EPG. Then you get the molecular geometry. And then you get the molecular polarity. And this is how important molecular polarity is when you look at something like this. So here, this is the molecular geometry, right? This is nonpolar. When you look at this, this is polar. And when we talk about polar versus nonpolar, so this is nonpolar, just your average molecule, and this one's polar. With the polar molecule, one side will be slightly positive and the other side will be slightly negative. And the reason one side is slightly negative is because there's more electrons on that side. And the reason one side is slightly positive is because there's fewer electrons on that side. So it makes this side slightly negative. This is the symbol delta.
And that's with the formal charges?
No, that's not what the formal charge is. Here's how I assign molecular polarity. You first of all have to know electronegativities. And remember that little chart I gave you? Where fluorine was
1.0 to
4.
1.0.
Yeah, oxygen was a 3.5. So the idea here is that if you look at the molecule, and here, hydrogen, by the way, is a 2.1 and carbon is a 2.5. So carbon's more electronegative. So in this molecule, you would say that the most electronegative atom is in the middle and the less electronegative ones are on the outside. So I call it an inside out. And for polarity, you don't want an inside out, you want a side to side. Now take a look at this. This nitrogen's a 3.0 and this hydrogen's a 2.1. That's pretty different, right?
Right.
So this nitrogen is the most electronegative element out of all 4 of these. So that means that this molecule, if I were to kind of draw it like this side is slightly negative, this side is slightly positive. So the 3 legs are slightly positive. The head of the stool is slightly negative. That makes this guy polar.
Okay.
And the way
And-
we demonstrate polarity is we usually draw a line next to the molecule that looks like this. Whoops. I'll do it over here. This is what we usually draw, an arrow. And you see how this arrow has a plus sign on it?
Right.
The plus sign goes on the slightly positive side.
Yeah.
Now, Issa, did I hear you voice a question?
No, no.
Okay. So for H2O, do you remember how I drew H2O like this? And put the lone pairs here?
Yeah.
Now look at oxygen, it's a 3,5, hydrogen's a 2,1. They're a most electronegative atom on one side of the molecule. Well, if I kind of draw a circle around this and draw this line through it, can't we say that this side is slightly negative and this side is slightly positive?
And when you say slightly, it's really that oxygen is more electronegative than hydrogen.
Right. So if I were to actually draw this, and I'm going to draw H2O a little bit differently, so maybe it's easier to see because I can draw it this way instead, right?
Yeah.
So the idea here is that when we look at the distribution of electrons, these lone pair don't really matter. But if you look at these bonding pair, the electrons are kind of like this. So the shape shows you where the electrons kind of spend more of their time. They spend more of their time near oxygen because oxygen can draw those electrons in better. So here, if they were perfectly even, so here you can see I'm drawing them perfectly even, right? Well, then you'd say, oh, that oxygen has 6 electrons, 0 charge. That hydrogen has 1 electron, 0 charge. This hydrogen has that electron, 0 charge. But this oxygen really has what looks like maybe not 6, but maybe 6.5-ish electrons, which makes it about like a minus 0.5 charge. And maybe these guys look like they have like 0.75 electrons, which makes them not have a full electron. So that makes them kind of positive, and they're like a plus 0.25 and a plus 0.25. Now these numbers are fake. But because the electrons are closer to the oxygen, it's going to make that oxygen more negative and the hydrogen's less negative or kind of positive. So Tony's method for finding out if the molecule is going to have a polarity is you look at your molecule. If you have a side that has your most electronegative atom, that's going to be slightly negative. The other side is slightly positive. So for instance, do you see this molecule here? So oxygen's a 3,5, carbon's a 2,5, hydrogen's a 2,1. Can you see that this side is going to be slightly negative and this side slightly positive?
Yeah.
Okay, so
Oxygen's the most electronegative.
right. And so the way we would actually draw this is this way. Now, what if I took this molecule and drew it like this? Then I draw the arrow like that. What if I drew something like this? This is a molecule called dimethyl ether. This is ethanol. And here you can definitely see that, oh, this side is slightly negative and this side is slightly positive, right?
Mhm.
I'm not putting lone pairs on this, but I should. So that's Tony's method of finding out if the molecule's polar or not. Can you find the most electronegative atom on one side? So I've shown you all these examples where they're polar, right?
Right.
So let me show you an example where it's not polar. The most electronegative atom is a carbon, but can you find the carbons on one side of this molecule? No, they're all over the place, non-polar. And here's another example.
So does that happen a lot with the octahedrals then?
No, because you don't have necessarily all the same atoms bonded to it. Can you see that the most electronegative atom here is oxygen?
Yeah.
Is the oxygen on one side of the molecule?
No.
No, so it's nonpolar. This is what I would call an inside out, where this is slightly positive, this is slightly negative, this is slightly negative. The inside is slightly positive, the outside is slightly negative, so it's nonpolar. Okay, but on the other hand, what about this? This is carbon dioxide or carbon monoxide. Does this have a slightly negative side?
Oxygen is more electronegative than carbon.
So that's what you draw.
Okay.
And how do you tell people? So this is what you draw if it's polar. What do you draw if it's nonpolar? You write the word nonpolar. You don't leave it blank. You say, oh, it's nonpolar. So to assign polarity, you just find the most electronegative side. If there isn't one, it's nonpolar. But all of these, it's hard to imagine, all of these are three-dimensional drawings. So you have to do the molecular geometry first. And usually we don't apply this idea to ions because ions have a charge. So they're attracted to the things that are oppositely charged. So what makes water so fantastic? One of the things that makes water so fantastic is that this molecule has this sort of polarity. So how would a water molecule interact with another water molecule? So remember, this side is slightly negative, this side is slightly positive. Well, if you had two waters that wanted to hang out together, this is the way they would hang out together. Because this one would have this sort of molecular polarity. This one had this sort of molecular polarity. And you can see that the positive would be attracted to the negative. And down here, the positive would be attracted to the negative. Because opposites attract, right?
Yeah.
So that means water molecules stick together pretty well compared to other molecules, which is why water is water at a room temp, not a gas.
That's interesting because they are the same, but it's just reversed.
Yeah, exactly. It's kind of like but it's because of their electronegativities that the opposites attract. So they stick together better that way. And there's a lot more going on with water than I'm telling you right now, but this is one of the reasons why it's a liquid at room temperature. And if you look at two ammonia molecules, where this is what you have, how would another ammonia molecule interact with this one? Well, it would have the opposite, because here you can, if I draw it this way, you can really see the opposites attract. So this is how they would kind of line up. And you got to imagine, I'm just showing you this in 2 dimensions, right? This would actually be more three-dimensional where they, they would all gather around each other. And so when they all gather around each other, probably the best way for me to show that to you is that. Whoops, slightly negative, slightly positive. And then another one here would be slightly positive, slightly negative. So they alternate, right? And if I drew another molecule here, what would I draw for the top part? Slightly positive, because opposites attract. And I don't dare try to do this in 3 dimensions because I'm not good at that. But this would even come forward out of the paper and backwards out of the paper. So, you'd have molecules behind here where this one would be slightly negative. This would be slightly positive, slightly negative. So that's my attempt at 3D. Okay.
Thanks, Tony. Can I take a screenshot of the first page?
This one? When you mean what first page precisely?
Yeah, or both of them.
Well, here, take a screenshot of that one. And then tell me when you're done. That's the last page. This was the second page.
Yeah, I'm done with the second page.
And this was the first page where we were talking about molecular polarity.
Yeah, so I just need that one. And I got that one. Thank you.
What I imagine you doing is taking a mental screenshot. So you're looking at this and you're blinking your eyes. Kind of like an I Dream of Jeannie thing. You ever see that show?
I wish if I could do that, then I could probably just take screenshots of my textbook. And
if you had that photographic memory, you could just blink your eyes and I got it.
Yeah, I would never have to worry about studying ever again.
Oh no, you'd still have to study. Just because you can take a mental shot of it doesn't mean you understand it.
That's true. It would probably take a long time to try to it'd be like reading a textbook while you're taking an exam, which is it's not gonna work.
Exactly. That's why most people don't like open book tests, because your professor can put anything on there because you can find it in the book.
You think people like it or don't like it?
Don't like it.
Yeah.
Every open book exam I've had was much harder than a non-open book exam.
The problem is that I feel like with an open book exam is that people tend to think like, oh, if it's open book, then that means I don't have to memorize things as much or study as much, and then it ends up backfiring because you're trying to learn as you're reading it.
Right. It's one of the reasons I explained the best way to study for this test is this material is to read a problem, especially ones where they show you how to do it, read through it, and then cover it up and see if you can do it without looking at the book. And if you can't do it without looking at the book, then you didn't learn it. And that happens with almost every problem that you read. You're like, oh, what did they do there? And then you figure it out. You don't want those aha moments during the test because it takes too long.
Yeah, it really does.
Yeah.
Are you gonna post up the homework solutions for chapter 7?
Actually, there is a Q&A that most of the homework is covered.
Oh, what, for chapter 7?
Yep.
Oh, I didn't watch that one. Okay, I have to go through all the Q&As.
It actually says homework, and it's like 2, 5, 6, 8, 9, 10, something like that.
Okay, yeah, I have to go through the Q&A.
I didn't post a solution because most of them were done in a video.
Okay, that's fine. I can do that.
So guess what happens if you call in tomorrow and you say, hey, what about the homework for chapter 8? Can we go over that? I would post a video of the solutions.
Yeah, chapter 8 is hard. I was looking at the homework for chapter 8.
Yep.
I'm still flabbergasted, but I will still Yeah.
You can do it. You've done it before. You had a previous chemistry class. They talked about this stuff before. It'll come back to you like riding a bike.
We shall see. All right. Thank
All
you,
right,
Tony.
Rebecca, Issa, thanks for calling in.
Thank you, Tony. Bye.
Have a good evening.
Good night, everyone.
Bye. Bye, Rebecca.
Bye.